Hey, good morning, everyone. I hope everyone is having a good time. So for just some logistics at first. So after the talk, we are going to have 10 minutes for Q&A. So please use that mic in the center. You can queue up there and then we can go from there. So for today's first innovation talk, we will have a talk about accelerating the development velocity of production machine learning systems using Docker. So please welcome to stage Canary and Akram from Pinterest.
Hi guys. Yeah. Hi, my name is Kinnari Jangla. I am manager at Pinterest. I work on the ads team at Pinterest, and I'm here with my colleague Akram Kochagunelli, who's a senior engineer, works in the home feed team at Pinterest. Today we're going to talk about accelerating development velocity of production machine learning systems using Docker. How many of you just woke up from a nap? Yeah, I sure did. This title is so long, so let me go ahead and explain what this talk is about. Accelerating development velocity is basically how do we make engineering for a developer efficient, or writing code for a developer in a way that it can speed the process. Code that powers production machine learning systems or services that back these machine learning systems with the help of Docker. So that's what this talk is about. And quickly, I want to give you some more context on what is included in this talk. There are two parts to this talk. One is the machine learning workflow at Pinterest, specifically in the home feed team, which Akram is going to talk about. And then the second part is in order to ship any workflow, any ML workflow or non-ML workflow, there is a bunch of testing required to ensure that your workflow works or your model works. And that requires debugging. And how at Pinterest we've created a debugging framework in order to engineers to be able to test their workflows with the help of Docker. So that's what this talk is about. And one thing to note so that you can get more out of this talk is even though we at Pinterest did this for machine learning workflows, this use case is very prevalent in Silicon Valley and can be used for any workflow, even for non-machine learning services. So just something to keep in mind so you could get more out of this talk. Cool. So moving forward. All right, anybody in the audience has no idea what Pinterest is? All right, so there are some people. Okay, I'm going to go ahead and quickly give a brief overview of what Pinterest is. Pinterest is a visual discovery engine, which means we want to help people explore content, explore new content, and discover ideas that they want to implement in real life. It's also a product which has 200 million pinners on a monthly basis. So needless to say, it operates at a very large scale. And Pinterest is also a lot about personalization. So your feed is going to be very different than your feed is going to be very different than your feed. So when we talk about personalization, machine learning comes to mind, obviously. So what are the different areas that we use ML in at Pinterest? Before that. Given the fact that we've come to becoming such a large product, I wanted to go a little bit into the evolution of Pinterest before going into all the different spaces ML is used at. So 2012 and before, Pinterest was this giant monolith service. We were a chronological feed where the user tells us what they're interested in, and we'd render the feed for you. Very simple, works for a small community of people oriented around similar interests, but doesn't really help anybody discover or explore content. So in 2013, we introduced recommendations where Pinterest would pick pins for the users. So if the user said that they were interested in baking cookies, we'd basically recommend that you might be interested in baking bread as well. So those are recommendations. In 2014 onwards, we introduced the concept of a smart feed, where we started rendering the feed based on relevance to you. So we started ordering the feed based on relevance to you. And then in 2015, we started taking user signal into account, where if the user liked something, we would show them more of that. If the user repinned something, we would show them more of that, and disliked something, we would show them less of that. And then 2016 onwards, we added more and more complex machine learning models, like tree-based regression models. We became more and more reactive. We improved our relevance, added localization. So needless to say, it became this giant product, and we had to go from a monolith service to all these microservices. So coming back to where the different places where machine learning is used at Pinterest, interest-based feed is what I just said. It's also known as the home feed, where the user tells us what they're interested in, and we render a bunch of pins based on those interests. Recommendations, as I said, Pinterest recommends what are the pins we think the user is very likely to engage in based on what the user has told us. Search is a very similar space. When you search for a search term, the results that are shown are also ordered in a certain relevance based on user signal from the past. And then ads, ads is how Pinterest makes money. That's where our revenue comes from. And very similar to our organic pins, we show advertisements based on what you've clicked in the past and what you're likely to click and buy from. And then visual discovery. Anybody here has used Pinterest Lens before? Okay, cool. So something for you to try out when you go back home. If you open your Pinterest app, on the top right corner, there's a camera icon. You focus that camera on any object, and it recognizes that object, sends you recommendations, and tells you where to buy it from, potentially. So that is also a machine learning space, where depending upon what the user has said is correct or not, we learn from that whether this is correctly recognized as the right object or not. So these are the spaces where we use ML. Now, Ekram is going to go a little bit into depth into how home feed is powered by ML. So I'm going to give it over to Ekram.
Thank you, Kinnari. Can everyone hear well? Okay. So let me start with a brief question. How many people use Pinterest and like their home feed? Oh, great, quite a few. And how many of you don't like your home feed? Okay, less, that's good. So we are responsible for the good and the bad content you're seeing on your home feed. And I will go deeper into what's going on behind the scenes when we are actually rendering pins for you. So let me start with some definitions. Pinterest home feed is basically what you see when you go to your app or go to pinterest.com. And it can show you your pins, but the first time you land, we basically make a blend of pins based on a few criteria. And the aim is to provide you an engaging experience. So a little bit more details. It's one of the most engaging surfaces on Pinterest and drives most of Pinterest revenue. And it was also the first product that we powered through machine learning algorithms. And as I'm going through the talk, one thing to keep in mind is our main purpose is to provide an ordering between the user and the items being our pins. So we will start at a high level and keep going deeper. And in the Q&A, we can go even deeper if you have questions around some specifics. So the content on Pinterest home feed can be shown due to a variety of reasons. The first one being is the topics you follow. So let's say you follow the topic of cute animals, and we have a whole bunch of pins associated behind every topic. The other one can be the users that you follow. So let's assume that you have followed this user with the name of photography. So we have a whole bunch of pins behind every user that they have pinned, and we also know the users that this particular user has followed. So we have a pretty good idea of the tastes and likes of the people that you're following. And the last one is, as you interact with Pinterest, we kind of learn what you like and what you don't like. So we also have this thing called recommendations, where we also discover your likes and dislikes. And ideally, the pins we have seen separately should be combined in such a way that you don't only get things from the topics you follow, you don't only get things from the users that you follow, but we make a nice and engaging blend of these things. So let's go a little bit deeper and look under the hood. The three things we have discussed are so-called our candidate generators. So the topics you follow, the users, and the recommendations we learn by your user behavior provide candidates that are usually in the order of a few thousand. And all these candidates generated by those candidate sources are fed into our ranking model. So that's where we keep the machine learning model behind our ranking system. Following the ranking model, we reduce these in the order of a few thousand pins into a ranked a few hundred pins, and they are fed into a policy layer. That is mostly where we enforce some business decisions, or if we have some restrictions around certain content. And at the end, all these candidates generated by different candidate generators are blended in a way based on how engaging we predicted them to be, and also based on what type of business policies we have. So in this talk, we will specifically be focusing on the ranking model. And before I go into the details of our current neural net model, let me give an overview of how our ranking model evolved. So around 2013, the very first home feed experience we were providing was mostly based on time order, so there wasn't much of a machine learning behind it. And the first model we launched was based on logistic regression, and it has provided orders of magnitude improvement over the home feed engagement metrics. In 2016, we moved into gradient-boosted decision trees, and starting from 2007, we are using deep neural nets. And in this talk, I will go a bit deeper into how we are doing that. Okay, so this is our current model, and let's walk from bottom to up. On the bottom, we have features around our entities in the system. So users, pins, the context in the system, and their interaction. And current feature count is around 700. They are fed into normalization and embedding layers. And following that is 4 hidden layers. And ultimately, we have a single output node, which predicts something called a pinability score. And that kind of gives us an indication of how likely you are to engage with a pin. And based on the output of the last layer, we rank the pins and provide them in your home feed. So the rest of the talk, I want to go over our model development lifecycle, because that is probably quite similar between different companies. And I want to highlight some of the things that I think are critically important compared to others. We will talk about 4 steps, and in the next slides on top right, you will see on which step we are talking about. So those 4 steps are basically data collection or any feature engineering work you are doing for a new experiment, followed by training your model offline and making sure that it's performing well. Those 2 steps basically compose your offline work, and following a trained model, we go into the online phase of the 4-step process. The first one is starting an A/B experiment, possibly with some limited traffic, to see what you saw offline is also holding online, so that you don't provide a bad experience in case your model was bad to most of your audience. And the last one is, once you see that your model is doing fine, you bump up the traffic and see if you have a good new model that you can replace your current one with. That being said, let's start with those 4 steps. So collecting training data, we have 2 main systems behind that. Let's start from left and walk towards the right. What we call feed view logs is in your home feed, anything you view, any action you take, we basically log that. And the positive actions are basically if you click on a pin or if you close up to see the image bigger, or let's say you like the pin so much and it's relevant, then you save your pin and that becomes a repin. Or let's say you clicked on the pin and you spent quite a bit of time with what was behind that pin. And that becomes your another positive label that we call long view, because you viewed it longer than a standard click. So having that label information, we also have quite a bit of knowledge about the user and the pin. And the user join and pin join are basically our systems that provide those features both during training and also during serving time. And we gather all our features and match those two. So at the end, we have our training data in the form of TF record, and that training data is basically all your features with the corresponding labels. Okay, so far so good. Like we just talked about what is going on in the system, how we are labeling our data. One thing I wanted to talk about collecting training data is there are some certain decisions that are quite important. One of them is what should be your labels, because ultimately whatever labels you provide to your machine learning algorithm and whatever you want to optimize for will be what the algorithm learns and will be what it predicts in the online setting. And the other thing is how you sample your data, because oftentimes you don't want to train your overall data, or sometimes you are not able to train on your entire data set. Those 2 decisions ultimately will also determine the scale of your training. To give you an idea, we are training on 14 days of training data, and that is to get rid of some time effects. For example, if you just restrict yourself to 5 days of the week, maybe you are missing, some of the good or bad days for your system. Based on our labels, our features, and how we are sampling, we end up about roughly 1 billion training examples to give an idea of our training data. Okay, I want to iterate a bit more on the labels and the sampling. Currently, we are separating our positive actions in 4 buckets. The reason being is differentiating your labels is quite important. For example, we have clicks. That's, we all know, like you click on the link behind the pin. We have long click. That is kind of an ad hoc measure we came up with because we want to differentiate things. Let's say you clicked, you didn't like, just came back. Whereas you clicked and then spent minutes behind that link. So we wanted to differentiate those 2 labels from one another. And repin is one of our strongest positive indicators that you like that pin, because you went into all that trouble of creating a board or saving that to one of your boards. So that was a strong indicator, and we make use of that indicator both during sampling and the training. And the last one is close-up. So that is kind of a soft indicator oftentimes. As you're scrolling, you saw one pin, you closed up to view it bigger and didn't click, just came back. So we could have ignored that, but it is still a positive indicator. It is better than just scrolling and not taking any action. So besides those 4, anything that we impressed but just got scrolled and you didn't give a response, we consider as our negative examples. And that becomes critically important because we also influence as we are training our learner by doing by applying some weights on our error measures. We will discuss about those in a little bit. Let me also spend some time on data sampling. So the first idea that comes is, let's say you cannot use your entire data, right? You need to do some type of a sampling. If you had done just uniform sampling, the chances are your core users who spend most of the time in the system, as well as the geography that you have the most users from, will dominate. So which can be a good thing or a bad thing based on what you want to do. But that means in that setting where we uniformly sampled, your algorithm will be learning or will be geared quite a lot towards your core users and core geography. So in Pinterest setting, we don't want that because the growth of your product depends on how engaging it is for new users and how well you are able to retain those. And not all new users are from the States. So that's why we have quite a few stratifications behind both user types and also our geographies. And we make sure that we represent them by certain percentages in our training data. Okay, cool. So now we collected our training data, we made sure that we are representing our population well, and now we are ready to train our algorithm. In the settings of Pinterest, we are training on single GPUs, those 1 billion some odd number of training examples, and it takes about 1 hour to finish our training. And most of our training code is in TensorFlow plus Keras. Just about a few weeks ago, we moved to automated training using Docker images. So what that means is oftentimes your training data collection, your offline training, and then evaluating your algorithm to make sure it is performing well on the test set are done separately. And that was the case with us as well. Although we had some automated scripts behind, it still needed manual submission of jobs or manual kickoff of the training. So instead we Dockerize all these code into Docker images, and now it is just submitting a workflow and everything is done in the background. We collect the data, then it trains your algorithm, it measures your offline performance on a separate test set and basically give you results already produced. So the benefit of this thing is it reduces human error. Like we have had cases where during manual submission we have accidentally changed the parameter, and we have quite many of them. And it becomes this whole adventurous debugging phase. Like you have your training data, you have your model, you have a whole bunch of parameters, and what went wrong where, right? It makes debugging easier, gets rid of manual errors, and also it makes better usage of our GPU resources. With manual submissions, we basically had standalone GPU machines, and oftentimes the usage is in bursts, right? Everyone wants to train an algorithm, so you have to wait, and when everyone is doing data collection or feature engineering, your GPU resources are idle. So moving to the Dockerized version of this, now we have a pool of GPU resources, and it is shared between different teams in the company. All right, so another thing I want to talk about, the second step where we do offline training and evaluation, is our training objective shifts over time. So remember we talked about the importance of defining which labels are important. We do use cross-entropy loss, but we don't just use the output of that to backpropagate in the neural net. We do apply different weights on each label, And most of these weights are hand-tuned. The reason why we do that is we want to make sure that when we make an error on repin versus a close-up, so the most strong and the least strong positive engagement, we want to make sure that the error we made on a more important label has a much larger impact on the neural net compared to a soft positive label. Speaking of error measures, you have quite a few of them. I just named some of the most common ones. And as you're choosing that, the most important thing is to align your offline performance with what you see online when you start an A/B experiment. For our case, we chose precision and recall AUC. And most of you may already know, but just to give you an idea, you can use it to compare two algorithms. And on one axis, you have your precision, and on the other axis, you have your recall. There is another version of the AUC, which is ROC AUC. It's between true positive and false positive rate. There are two reasons why we opted for this one. The main reason is that it aligned pretty well with our online results. So that gives us an indicator that whatever we are seeing offline will also be replicated when we start an experiment. So we won't be seeing a big surprise, or we won't be giving users a pretty bad experience. And another reason is compared to ROC AUC, if you have a class imbalance problem, which oftentimes in online systems you do, you have much larger amount of negative instances, the precision and recall AUC works much better because it doesn't necessarily take into account the large amount of negatives. All right, so let's revisit this back. Remember, in the first one, we have started with manual processes in our offline steps. Now we have a Dockerized version of this, and basically the whole offline step is just one submission of a job, and you wait more than a day, and then you end up with the offline results showing how good your new algorithm is expected to perform. Cool, so let's say now we have our algorithm, we know that it performed well offline, and what do? We start an A/B experiment. We can talk quite a bit about A/B experiment and different aspects, but what I wanted to emphasize for this talk is it is often difficult and can be quite misleading to find a single metric that you expect to give you a very good overview of what's happening. So kind of a one metric to rule them all. Instead, in Pinterest, we focus on quite a number of different metrics. The most important ones are how are our labels doing? In other words, with the new algorithm, are we improving the number of repins that the users are making? Are we improving the clicks? Or oftentimes we see a trade-off. Let's say you give up on clicks, but you get quite a bit of repins. So what does that tell you? And the other thing is, with the online A/B experiments, your core users may be dominating the effect that you see because they interact so much with the system, and your core geography, since it has so many people behind it. We also take a look at how we are doing for different user groups and different geographies. So we make sure that as we are improving our metrics, we are not hurting other local countries that don't have as much users. Okay, and the last step is, let's say we did our... Can you hear me? Okay. We did our A/B experiment, and we saw quite good results. And now we replaced our production model, and we are serving our new model. I grayed out some of the services that are not relevant for this talk, but this is pretty much what our system in the background looks like. So whenever you interact with the system, it starts with an API call that directly hits something called Smart Feed Service. And Smart Feed Service is responsible for gathering all the content and providing an already formed homepage experience to the user. And how Smart Feed Service does that is it calls smart feed generator, which talks with our candidate generators we have seen at the beginning of the talk. And they passed the smart feed generator a few thousand of their best candidates. And in the smart feed generator, we do the ranking and pass a few hundred back to the smart feed service. And through the API, you see the pins that are exposed to you. So at this point, I will pass it to Kinnary again to talk about how we are using Docker behind each of those services.
Better? Yeah. Thanks, Akram. Random slide. Any guesses what this is? When I presented this in my company, some of my teammates said this was the food in the cafeteria. So I was like, I don't know what you're eating, man. I mean, seriously, donkey? That's got to be another level of food. But anyway, these are microservices. And this is a great analogy that I like to give. As you see, they can't talk to each other. They don't know where to get the input from. They don't understand each other's language, operate in totally separate environments. So getting back to the previous diagram that Akram presented, this is a very simplified version, obviously, of how the whole home feed system works. And we have many such systems at Pinterest. So in order to get this up and running, or rather ship a certain workflow, when the model is deployed in the smart feed generator service, you'd want to test this whole thing. And so in order to test this, you'd want to get all these services, a bunch of these services up and running. So what do you do when more than one service depends upon the same dependency, but a different version of the dependency? I mean, I don't know any developer, I haven't met a developer so far who hasn't run into a dependency hell. So what would be the solution for that, right? How about isolating these applications that depend upon different versions of these dependencies into their own environments, packaging it up, and running all of these separate applications on a machine? But how do you do that? And that's where we created a debugging framework using Docker at Pinterest. So now, needless to say, it's not just one service. In order to test something end to end, in order to see whether your model works or not, you'd want to get all these services up and running. And so how do we do that? We put a very simple usage of Docker into practice using Docker Compose. And that's what a sample Docker Compose file looks like, where we're just connecting all services one after the other, linking them to one another. And what basically happens is when you send a request to one service, if it actually goes to another service, it hits production. In this case, it'll hit the Docker container for that service. I'm going to go and give you a demo. But who has heard of Edward Murphy? He said anything that can go wrong is going to go wrong. And so I took that very seriously. And I'm going to show a video of my demo, so nothing can go wrong. And I decided that only yesterday. So let me show you my video, if I can get this working. Cool. Oh. How do you get there? No? Here. We saw it there. It's okay. Yeah, but I don't see it on this. Oh, there you go. Perfect. Okay. I'll take it from here. Thanks. Sorry about that glitch, but can you all see the font? Okay, perfect. Sorry, I'm really short and I can't see much. So I'm going to just make sure that the view is proper. Okay, let's start this. Cool. So this is basically showing you a view of the Docker Compose file. And as you see, I have added a few of real production services in this file, Pinnacle 2, Fantasio, and Magicbox. And then if you see further, Pinnacle 2 links to Fantasio and Magicbox, which means that any request that goes to Magicbox and Fantasio in production would now go to the Magicbox and Fantasio that runs in the Docker container. And then Fantasio links to Magicbox here. Going further, just using Docker Compose up gets all these services up and running. We actually do this on a daily basis when we try to debug our workflows. And if you see here, Magicbox server has started running on port 8821. Pause this so you can see it right here. And now Pinnacle 2 has started running on port 9996. And if I just do Docker P as quickly, I see the two containers. They're up and running. If you notice, Fantasio crashed. That service crashed. That was intentional for the demo. So you can see that container is not up and running right now. So that's one way to see what are your services that are actually up and running and what are the ones that are not running. Go ahead and debug them, get into the container, yada, yada, yada. But anyway, that's what I have for the demo. And getting back to the presentation. Okay. Cool. That's what I have, but if any of this interested you, please check out Pinterest if you haven't yet via Pinterest.com or our app. Don't forget to check out Pinterest Lens. That's my favorite feature. We also have our engineering blog, and we're probably going to post this video on our engineering blog as well. See your home feed or create a business account, promote your pins if you want to. I've also done a podcast on Software Engineering Daily. It's the same title, or you can search for our names and you'll be able to find this topic in a little more detail as to how Pinterest does it. And I'm also writing a book on Docker for microservices, which is going to be published by Apress, due in July. So if you're interested in this, keep an eye out for that. But otherwise, I am at Kinnary@Pinterest.com and Ekram is at Ekram@Pinterest.com. So feel free to email us or hit us up for any questions that you might have. But for now, we'll open it up for Q&A. If you should go to the mic.
Or I can repeat it.
Hi, everyone. Please use the mic on the middle, but I can pass this one as well.
Hi, yeah, so my question is, you earlier were showing us how one given model might improve certain metrics that you're looking for across your platform, but do you apply different models or metrics, say, for example, in one user segment, if it gets the result that you're looking for, but it might not work well in, for example, Ukraine or something, but so is there a way where you segment your traffic so it just doesn't use that model, or you'll use different models for different segments?
Mm-hmm. Yeah, that's actually a great question, and one of the is it working? Yeah. Okay. Let me also repeat the question. So the question is, if you want to optimize better for certain users or certain geographies, wouldn't we be better off if we were to train separate models for these? And the question is most likely yes. And that's an area we are currently working on. So that is pretty much like what I will do once I go back to the office. The problem with multi-models is it becomes very difficult to maintain all these models, right? So currently, to change your production model, you train, you test, you see the performance of a single model. And imagine you repeated that for all your user groups across all your geographies. It would be hundreds of models, and it would fairly quickly become unmanageable. One thing that we are trying at the moment is called multitask learning. So remember how we had a single output node that was, across all users, across all action types. So we have plans to separate these out into multiple nodes, and every node will be like a separate model. So one node will be predicting for repins, one node will be predicting for clicks. And at the initial stage, we just want to do it for action types. And they will basically share the same hidden layers. So what that means is they will be able to communicate through the hidden layers, whatever they are learning for each prediction. And once we have seen quite good results with that, once we replace our current model with that multitask model, we will move to adding, different nodes or trying out different architectures for geographies and different user types and so on. Yeah.
Hi, I had a bunch of questions. The first thing was the size of the Docker images that you use in general. Like, how much is the size approximately? The next question was, what are the best practices for persisting your model from a Docker perspective?
Sorry, I didn't understand your first question. Can you repeat that?
The size of your Docker images on an average, and what are the best practices for persisting your model from a Docker perspective? And the third question I had is, do you use serverless technologies in your infrastructure at all?
Yeah, so Docker images really depend from service to service, the size of that. Also, one thing to note that we haven't productionized any of these services in Docker yet. So honestly, the size, what the question you're asking is how would that be handled in production? That's not the problem we're trying to fight yet. This is mostly a debugging platform. So also sometimes developers share these images from a common space, so size doesn't become that much of an issue. And then your second question was?
Some best practices you do for model persistence.
For model persistence? Do you want to take that?
Sorry, can you repeat the question again?
Best practices for model persistence from a Docker perspective, like where do you store it? How do you share? Because you're operating with a lot of automated training. So where's the, how do you have any best practices for persisting it?
Yes. So the question is like, what are some of the best practices we learned along the way as we Docker our
anything,
training? Yeah. So let me answer it in two forms. The first one is your production model. Maybe if you move into a continuous learning framework, what that means is you retrain an existing model over and over again. Let's say you retrain it daily starting from previous day's model. So it makes that scenario very simple because now there is no human intervention. We can use the same image of the production code and keep iterating. So every day, you have a new copy of your production model that trained on new data. The second one, the best practice we have seen is we have multiple images of our code. One image is for the production model that keeps learning based on your new data. And the other one is as you're experimenting and changing the code, you can create your own image with new features or changes to the model trainer code. And you are not impacting anyone or you don't have to worry about checking in your code. You just work on your own image. So that was kind of the two best practices I believe we have learned.
Thank you. And the third question was serverless. Do you have anything which is Lambda or which is serverless in this whole, like for scoring, for example, you load a model, you just want to score against a model. Do you use serverless technologies?
It's echoing quite a bit.
Serverless technologies. Well, the answer to that is, like I said, that we're not in production yet, so that doesn't matter at the moment. But for debugging, we don't. We're just basically starting off creating a debugging platform. We're also going to use Kubernetes eventually as an orchestration platform. But in the production system, we haven't thought of the serverless technologies yet.
Sure, thank you.
Thank you.
One last question.
Hi, thank you. That was a great talk. I'm curious, how do you track the performance of your models sort of within your team? Is there a system that you use for doing that?
How do you track performance of your models?
So the performance of the question is how we are making sure the models are performing well, or how we are tracking their performance, right? So there are two important aspects. The first one is how do you know your model is good that you should start directing actual traffic to it, right? And you will see some discrepancy between your online users and what you got offline. But the idea is we make sure that our test data that we are evaluating offline performance is representative of what the algorithm will see online. And that's where, all the stratification and label definitions and like selective sampling comes into play. Offline, once we are sure that they have comparable or better PRAUC performance in each of these segments of users and geographies, we have a pretty good understanding that it will be fine online. And in the online, one thing we do is we don't ramp it up to significant portions of traffic, because sometimes it can be the case that your online and offline data diverged and your model will not perform well. So for a few days, up to 3 days, we run it at small traffic and make sure that it is performing well. Then we ramp it up to a considerable traffic to get statistically significant results. Yeah. Cool.
Thank you very much. Great talk. Please give a hand of applause to them.
Thanks, guys.
Thank you.